Okay. um, we're missing Taylor today. Taylor could not be here today, but we do have some things that we're going to do, some seat work that you're going to do today. I mean, I've got some problems for y'all to solve as we go through the notes. So I'll be relying on you a lot because it's going to be hard for me to get to everyone. So when I'm helping, or watching you guys. So really ask you to make sure that you're sharing with your neighbors, right, or asking questions of your neighbors when we're doing these, when we're doing any sort of problems as a class today, so that everyone will hopefully, be able to get through the activity. I've added a little bit to the homework, right? So notice the first homework is missing now because the due date is passed, right? You can, I think, go back and look at that, though, through this button. Now, tomorrow or something like that, I will turn the answer key on. So for that first homework assignment. So if you're curious about a problem that you didn't get correct for some reason, you can go back and look at past assignments. And when you open the assignment, I think when I get the answer key turned on, the answer key will be turned on, so you can see what the correct answers are. But I haven't done that yet because I'm still waiting for people who may be using an extension, right, to continue working on that assignment. Now, this assignment was already there, right? The one on integration. So we're going to talk about integration today, hopefully, quite a bit, but we'll see how far we make it. And then, I'm sorry. We started talking about integration last time, and we're going to continue talking about integration. So hopefully we'll finish those notes, and then let's see if we can get to this next section, exponential functions. Notice I'm skipping a section there from 5.2 to 5.4 because we're not going to explicitly cover this section on inverse functions. This is really not a section about calculus. It's really an algebra section, just reminding people about how inverse functions work. So you are probably already familiar with the things that are in section 5.3 about inverse functions. Inverse functions are really important to this class, though, and so that's why this section is there. But so I've just posted some problems from that homework as extra credit. Again, you're probably familiar with how to do these problems from past courses, so this is just an extra credit assignment for you. However, there is, in that assignment, I had forgotten, so by the extra credit, you get, you can earn flux dollars. I think that's under the description, yeah. So if you open the description there, it says you can get 5 flux dollars if you do this assignment 80% or more, okay? It's not that long. I think it's 8 problems, so it's really pretty easy to get the flux dollars here, okay? Now, there is, however, an actual lecture on inverse functions. So if you can look at this video. This is a full-length lecture on the topic of inverse functions. So this would be like a lecture on inverse functions you would see in an algebra class or a pre-calculus class. So you can't look at that, but you probably don't really need to look at that. You can probably do the problems just from your past knowledge, your past experience with inverse functions. Not this one. These are from the book. I guess you can look at those. Those are book videos. This is me talking in this video. Okay, so all right. So you've got that extra credit assignment. It's not due until the time of the test. We're not going to refer really to things explicitly from that assignment. Okay, but again, we are talking a lot about inverse functions. So. In this class, so we will be referring to them frequently throughout the whole course. All right, let's get rid of that. Whoops. And then, then there's the new assignment, this one new assignment, right? And then, of course, the calculus viewer is still there. You all did really well on the 5.1 assignment, so almost everybody worked on that assignment, and the class average and the class median were really high. They were in the 90s, so that's excellent. So that's a really good sign. So you want to keep up that momentum. So you now have an actual grade in the grade book. When you go to what is it? My Grade. Where is it there? Okay. When you go to My Grade, you'll see an actual score there, right? It's going to be the same, and there it is. Okay. So it's my total, but it's going to look like. It's going to be the same grade as your first homework assignment because that's the only thing you've got in the grade book so far, right? Okay, but you do have a grade there now. Currently, mine is 0 because I have not done any homework. All right. Bad for me, but good for you guys. So as long as, again, you were not, as long as you were not relying on, artificial intelligence, right? Okay, to too great a degree to help you with that homework number 1, or maybe someone else's intelligence, right? A friend of yours' intelligence too much to complete that first homework assignment, then that's a really good sign, okay? That really lays the groundwork for scoring well on test number 1 when that comes up. So, and actually really lays the groundwork for doing well in the rest of the course, because a lot of the things in that assignment we're just going to continue, okay, in one form or another throughout the course. So that's great. But let's keep up the momentum on this integration homework. Okay, you guys have any particular questions right now before we launch into something new here? Yes. Oh yeah, Calculus Flux. So remember, Calculus Flux is the dollars, right? Yeah, that you can earn for various things. So I have not yet entered any Calculus Flux totals. So some of you may have already visited either the Academic Support Center, North 925, or you may have gone to see Taylor, and so you have earned Flux dollars, but I haven't put those in yet, but those will be in there shortly. And it's a little bit hard to, how do you do that? I think you go to get to the Flux, to see your Flux total. Well, this is the way I know how to do it. Let me see. If we go to My Total, will this do it? Yeah, go to My Total and then go to Raw Scores, and then it will show you your Calculus Flux total. There may be another way to see that, but that's how I know how to get to it. So this will be what your Flux total is. Okay. Out of, I put 200. I don't know how many total Flux dollars someone can earn, but I don't think it's 200. So those will just keep accumulating through the semester as you either go to tutoring or do well on your tests, or the various other ways, right, that you can earn Flux dollars, right? Okay. So, but don't expect to see anything there yet. Okay. Can I get back out of this? Yeah. All right. So I had another question. Was that the same thing? Yeah. Yeah. Okay. That's what it is, right? So it's there. That'll just be there all the time. Is there a due date listed on it? Yeah, but it's not till the end of the semester. But it's not really an assignment that's due, right? Yeah.
For the Flux dollars that say not about attendance policy.
What now?
There's one on the syllable that say not violating attendance policy.
Yeah. So what is the attendance policy? Very simple. No, not 6. Okay. Yeah, 4. Right. Yeah. If you don't miss more than 4 classes, then you have not violated the attendance policy. Right. Okay. So for that, you earn 25 Flux dollars automatically, but that won't show up until the end of the semester because I won't know, right, until the end of the semester how many you've missed, right? Now, one thing I forgot to mention is there's another penalty for violating the attendance policy. It's not just losing the Flux dollars. If you violate the attendance policy, what says in the syllabus is the maximum grade you're going to get is a D, okay? Now, you can appeal that, however. So if you are having to miss for, legitimate reasons, and it runs to be more than 4, then, you'll have to come talk to me so that we can, extend that. You won't get the Flux dollars in any case, right? But you can avoid the automatic D. The reason I'm not trying to be punitive here. The reason that I'm doing that is I've had experiences in the past where students miss like half of the classes. All right, okay, and they miss half the classes. Literally, they miss half the classes. So, and then when they don't get a passing grade, then they come to me and complain, why did I not get a passing grade? And I'm like, well, it's because you missed all these classes, and then your average turned out to be, because you didn't know the material, because you missed all the classes, and your average turned out to be 60, right? So that's not a passing average. There's nothing I can do about that. But the reason that you had a 60 average is because you weren't coming to class. If you'd come to class, you would have earned better scores on your tests and your homework, right? So that's the reason that is there, okay? So it's not to punish you if you are ill or have family issues and you have to miss a lot of classes for some reason, then come and talk to me about that, okay? All right. But that's really unusual I have very few students who are still attending at the end of the semester. Some people stop coming, right? But if you're still people who are still attending at the end of the semester, almost no one violates the attendance policy. That's really unusual. Okay. Other questions about that? All right. Okay. All right. So again, Taylor's not here. So, but I'm going to start the class roll right now. So remember, sign in the correct spot. I think everyone is accounted for. So I think everyone has been to class at least once. So I've got the prior rolls attached. So make sure you're signing in the right slot, right? Okay. I do have to ask for one person. Is Gabriella here? Gabriella Maldonado? Is she here? Okay. All right. Okay. So let's go back to our notes from last time, and this is about where we had gotten to last time when the machine died. So I hope the machine won't die today. Remember, we were trying to integrate secant squared x over tangent x, and we had essentially finished. So I went ahead and filled that into the notes. There's the final antiderivative there, natural log of tangent of x plus a constant. Okay. So I think we got to this step. So I just wrote the last step that we missed last time. And all right, so that brings us to this example, which is a very similar example to the ones that we were doing last time. Okay, so we're going to integrate this expression, this rational expression, this fraction, and probably that's going to involve natural log because that's what this whole section is about, right? Okay, but in order to assist you, you might want to try using integration by substitution. So you may want to let the variable u represent some part of this integrand, and last time we were always letting u be what? The denominator, right? Okay, so let's try that procedure now. So following that suggestion, let's let u be the denominator, right? Okay, and then let's see if we can go through the steps of integration by substitution and see if we can end up with an integrand that we can easily integrate, right? And then get to the final antiderivative for this. Okay. So again, I'm gonna let y'all. I won't be able to talk to everyone, but I'll walk around. But be sure you're talking to your friends, right? So that everyone at least gets off to the right start on this, even if you don't get it sort of completely done, right? Because we'll go through it on the notes, but I want to give you a chance to sort of remember what we were doing last time before we crank up again. We've got some kind of more complicated examples today, so it'd be nice if we could get this one. Did you get it there? Let's see. All right. So dx is this, right? So can we do something with, can we somehow, remember this is u, right? So you want to write that as u. Now is there some way that we can continue here on this one? Can you look at that one? Can you factor that one?
Yep.
Yeah.
Okay, that's
Right, okay, yeah. Perfect. That was fast. Okay, all right. What now?
Okay.
Yeah,
No,
no.
just factor in the.
Yeah, well, you can factor this a little bit. What can you factor out something here from 2x plus 2?
Okay.
Yeah, you can factor that, and then that's gonna, then you'll be able to maybe reduce really nicely there. Did you get it already? Okay.
Am I doing it right? So it's gonna be 1 over 2 du equal to x plus 1, and then that
Where's your dx though?
my dx is right here.
Oh, I see. Okay, yeah. So don't leave off your dx, right? Yeah.
That's right.
I think that's right. Now solve that for dx though. Okay. Oh yeah, so that's really fast. All right, so now, all right, yeah, there you go. Because how did you get to this though, so fast?
Cancel out those.
What now?
We cancel out those, and that's half.
That's half, right? Yeah. Okay. Don't forget your integral sign though, right there. Correct? Yeah, that's still there. What'd you get there? Yeah, that looks good, but you're missing a constant. You're missing a constant. Because what was the derivative here?
2.
Yeah, 2x plus 2, right? So what happened to the 2? Somewhere there's still a 2 hanging around. All right, so now you know what dx is. So now you can substitute that back in here. You know this is u, and then there's going to be some reducing that will help you a little bit. That's always what you're hoping for, is some reducing there. All right, so what happened to the 2 though?
Take out the 2 right here.
Oh, you took out the 2 right here,
Yeah.
but that won't go out as 2 in the top because this 2 is in the bottom, right?
Yeah.
So isn't that going to go out as, I don't think that's going to go out as 2. I think instead, I think it goes out as 1/2. Be careful about that. How far did you get there?
Not very.
Well, you're on the right track. That is du dx, so solve for dx. So what's dx? So we're going to solve for dx here. Yeah, so you multiply both sides, right? So you have du is equal to 2x plus 2 times dx. Now you need to divide by this because you've got to isolate the dx. So you have to have dx equals. And then you can plug that in for dx in the integrand. Okay, yeah. That's the steps.
So I'm confused.
Yeah. Right. So you took this 2. You're writing all over the place, though, so it'd be helpful if you would keep your integrand somewhere, right? Okay, but what? Yeah, it's hard for me to follow what you're writing here. Is this it? Is this it? But this should have an integral in front of it, right? Yeah, this has an integral in front of it, right? Isn't all of this the same as this? Now, look, you'd like to get rid of these 2 things because that's going to slow you down, but how can we reduce that? What can you factor out from here?
You can take 2 out.
You can take 2 out, right? So that would leave you with what?
X plus 1.
Yeah, perfect, right? And then they,
Let's be like we kind of left out the 2
yeah,
on this one, so
right. So now you can divide that out, right? And that's exactly what you want. But the 2 you can also factor out, but it's in the denominator. So be sure you factor out in the denominator. So you're not factoring out 2, you're factoring out what?
1/2.
1/2, right, yeah, okay. So you end up with 1/2. These are gone. This is gone, and you just have du over u. But that you can integrate easily, right?
Yes, that's I think 1x, right?
It's integrate.
ln.
Yeah, L and U, right, that's correct. Yeah, okay, exactly. Oh, all right, so y'all, oh, wow, y'all did that really fast. Oh, okay, I'm going to have to make the class a lot harder, okay? Keep y'all's interest here. Okay, so I didn't get to everyone, but a lot of people were doing really the right things. Okay, so So remember, du dx, right, is going to be 2x plus 2. And now you want to solve this equation for dx. So when you go through the steps, a couple of steps here, you end up with what? Dx is du over 2x plus 2. Is that correct? Yeah, and now you can do your substitutions, right? So now you substitute. So you have x plus 1 over, remember all of this is u, and then times dx, though, is du over 2x plus 2. Now at this stage, at first, we might be a little bit disappointed, right? Because what I'd like to happen here, sort of my goal in all these integration problems, is I'd like to have a lot of cancellation at this point. So I'd like these things to cancel, right? So that all the x's are gone, and I just have an integrand left with u. But initially, it doesn't look like that's going to happen. But we don't want to be hasty, right? Because remember, from this expression, what can you factor out? 2, right? 2x plus 2 is really 2 times x plus 1, correct? So you can write that as, instead of 2x plus 2, you can write this as 2 times x plus 1. And now the x plus 1s divide out just like we want, right? Remember, you still got this 2 here, though, that you factored out. That's in a denominator. But you can factor that out of the integrand. But it factors out as 1/2 because it's in a denominator, right? So you have 1/2 and then antiderivative of du over u. That's all that's left behind the integration sign. But that is an easy antiderivative, right? That, we know, is the natural log of the absolute value of u. That was our goal here, right? Was to take that complicated antiderivative and get it down to something that's easy like this one. And that one's easy. So, and now we're done. All we have to do is undo the substitution, right? Because u is x squared plus 2x. That's the sort of outcome that we're hoping for when we do integration by substitution, right? Okay, that things will sort of simplify when we do the substitution, and the we'll end up with an integral that's easy for us to figure out what the antiderivative is, right? Okay, so this one works out nicely. Let's do another pretty simple example, but just with a little extra complication. So let's evaluate a definite integral, not an indefinite integral where you don't have limits of integration, right? That's just finding an antiderivative. But let's do a definite integral instead, where we have limits of integration. So let me scroll down here and look at this example. All right. So here we want to find the area of the region bounded by the graph of x over x squared plus 1. This is x over x squared plus 1, so I drew a little picture of this. And the x-axis up to x equals 3. It turns out that this curve goes through the origin on the x-axis. So you would start your region here, and then up to, it says stop at x equals 3. So we're looking for the area of this shaded region below this curve. You know now how to set up that problem, right? Okay, that's just a very basic calculus 1 problem. You can calculate that by that area by calculating a what? A definite integral, correct? Okay, a definite integral. That's an integration problem, right, where you have limits of integration. What are our limits of integration here? 0 to 3, right, okay? Because this region extends from 0 to 3 along the x-axis, correct, right? And then you just write the formula for the curve, right, okay? That is the integrand of your definite integral. So you get x over x squared plus 1. That's it, okay? All right, now, how is it, though, that we evaluate a definite integral, okay, as opposed to an indefinite integral where we're missing the limits of integration? That's the fundamental theorem of calculus version 1, not version 2 that we used in the first set of notes, right, when we were developing the natural log function, but the more familiar version of the fundamental theorem of calculus. That's version 1. And the fundamental theorem of calculus version 1, which I actually have in the notes, but I scrolled past that, okay? What that fundamental theorem says is, if you're trying to evaluate a definite integral, right? If you want to evaluate a definite integral like this, what you have to find is the antiderivative, right, of your integrand. You have to find the antiderivative of x over x squared plus 1. And then what do you do with that antiderivative once you found it? Yeah, you plug in the limits of integration, correct, and take the difference, right? So to evaluate this definite integral, we're going to take capital F of 3 minus capital F of 0, right? Where capital F is what? That is an antiderivative, correct? So if you want to kind of break this down into a step-by-step process, you don't always have to, okay? I'm just going to take it very slowly here, though. If you want to break this down into a step-by-step process, there are 2 steps here. First, find the antiderivative of x over x squared plus 1. In other words, find just the indefinite integral of x over x squared plus 1. And once you found that, then the second step is to do the arithmetic. That's where you plug in the limits of integration, okay? So let me break it up into these 2 steps. But often now, in practice, you can combine these 2 steps, but I like to think of them as separate, all right? So here's step 1. I'm going to find the antiderivative of x over x squared plus 1, right? So in other words, I'm going to compute this indefinite integral. And then once I find that antiderivative, then I'll plug the limits of integration in, okay? Right? All right, well, let's see. All right, so let's see if we can find that antiderivative. Okay, so that would look kind of already familiar to us, right? What do y'all suggest we do? What now? Substitution, right? Yeah, let's try substitution. Right? I mean, it looks like exactly like all the examples, right, that we've just been solving, right? So it seems like substitution there will be a good method. And what substitution? U equals what, though? Yeah, the denominator, right, because we're hoping that we'll end up using a natural log to find the antiderivative, correct? Well, let's see. So when we do that, we get what? Du dx is, that's not too bad, 2x. So what's dx there? Is that going to be du over 2x? Is that right? I skipped a step, but when you solve for dx, I think you end up getting dx is du over 2x, okay? And now you just do your substitution, correct? So let me write it over here. So we have the antiderivative x over, remember, x squared plus 1 is u, times du over 2x. And are we lucky now? Do we feel lucky? You know that Clint Eastwood movie, right, where that's his famous line. Do you feel lucky today? Okay, so are we lucky today here? Yeah, right, because the x's are going to cancel, right? So that's what we're hoping for here. So the x's cancel, and we have the 2, but remember we can factor that out, right? So we get 1/2, and then antiderivative of du over u, right? But now I know what that is. That's natural log of u, right? So I have 1/2 natural log of u. And then plus the constant, and then we undo the substitution there. Let me write it down here. I'm running out of room. So I have 1/2 natural log of, what was it, x squared plus 1? Yeah, there we go. Okay. So that's just 1/2 of the problem now, right? That's step 1. But we found the antiderivative. Now we use that, right, to plug back in the limits of integration. But the rest of this is arithmetic, okay? The hard part was finding the antiderivative. Now the rest of this is just doing arithmetic, except it involves a natural log, so we may have to have the calculator help us. But anyway. All right, so let's finish it off. So finally now we know that this definite integral, right, the definite integral from 0 to 3 of x over x squared plus 1 is going to be, you take your antiderivative, right, and so that's 1/2 natural log of the absolute value of x squared plus 1, right? And remember, you plug in, what, 0 into that, right, and 3 into that, and you take the difference. The way you indicate that on paper is put this antiderivative expression in brackets, right, and then write the limits of integration over here on the right, okay? And that means plug in the 3, plug in the 0, and take the difference, okay? So let's see what happens here. So when I plug in the 3, I get what? 1/2 natural log of 3 squared plus 1, right? And then when I plug in the 0, I get 1/2 natural log of 0 squared plus 1. Oh, what happened to the constant, by the way, that was in the antiderivative? Oh, right here. Notice that didn't show up down here, right? Yeah, when you're doing a definite integral, don't forget that you don't need to worry about the constant in the antiderivative, in the antiderivative, right? That's not necessary. So we just drop that, okay? When we're evaluating the antiderivative at the boundary values, we don't need to worry with the constant. All right, well, let's see what this arithmetic is. So we get there, what is it, 1/2 natural log of 10. Absolute value of 10 is still 10. And then what happens here now? This is 1/2 natural log of 1, right? But what is natural log of 1? 0, right? Okay, so there's one value you definitely want to remember. Remember, natural log of 1 is 0, okay? So this is 0. So that's very convenient, right? So there's our answer. It's just 1/2 natural log of 10, okay? And if you want to estimate that, right, you can do that with your calculator just by evaluating or just by estimating natural log of 10, right? Okay, so that's what that area turns out to be. What is 1/2 the natural log of 10 approximately? What now? 1.15? Okay. All right. So that area is about 1.15. That's does that make sense to us? I guess so. That's kind of a long area, right? Okay. But this curve is not very high. It doesn't even go up to 1 on the y-axis. So that looks like that's a plausible answer. By the way, what's the area of that? If you filled up this whole rectangle here from 0 to 3 and from 0 to 1, what would that area be? This whole rectangle. 3, right? 3 times 1, right? Length times width. So it would be 3 times 1, but we only have a little piece of that, right, that we're actually shading. So 1.15 sounds like that could be a plausible answer there, all right, to that for that area. All right, so there's just a quick reminder, right, of how one evaluates a definite integral. I know you've done that lots of times, but just wanted to remind you of that, because it's going to come up, you know, from time to time, right? Okay, now we get to, now we're going to step it up a notch, okay, because we've looked at kind of the basic examples of using the natural log to help us integrate, but now we want to look at some of the more advanced examples, okay? So these are, well, they're more advanced examples, what can I say? All right. So they're not definite integral problems. This is just an antiderivative. So we want to find the antiderivative of this, x squared plus x plus 1 over x squared plus 1. Okay. All right, now so, you know, our initial thought here might be that, you know, just to try this substitution, right, u equals x squared plus 1. Just like we did in the prior example, right? Okay, and then we get du over dx is equal to what? 2x, right? Or dx is equal to du over 2x. But when you make that substitution, you know, nothing happens like before, right? Okay. Because well, this is u, right? So this is u, but dx is du over 2x, and see, things just don't simplify anything like in the prior example, right? Okay, you know, we wanted this and this to cancel, but that's not even close, right? That's not even close to canceling. Okay. So I'm going to show you kind of a little trick here that we're going to play on this problem. And this trick works. Doesn't always work, but if it's going to work, okay, it'll work in situations exactly like this problem. So if you look at you have to look very carefully at the integrand here. So we have x squared plus x plus 1 over x squared plus 1. This is a polynomial. Okay, that's a quadratic polynomial, x squared plus x plus 1. And this is also a quadratic polynomial. Now, if you recall about things that you learned about polynomials, polynomials have degrees, and the degree is always the highest power of the unknown, correct? So this has degree 2. That's what makes it quadratic. A degree 2 expression is a quadratic expression. And this one also has degree 2. All right, so what we have here is a degree 2 expression divided by a degree 2 expression. So when you're facing an integrand like that, okay, one thing that sometimes helps is if you do long division. Now, have you all seen long division with polynomials before? Yeah, I know you have. Okay, if you just got out of pre-calculus recently, okay, that's pre-calculus here recently, but probably anywhere, you or sometimes it's in algebra classes, you will have seen long division with polynomials. Okay, so we're going to use that process here. So you probably thought I will never use long division with polynomials. Okay, but now you are. All right, it comes out in really handy right here. All right. Now, but here's the important thing to remember. You've got to remember the long division process, but we're gonna practice that. But the other important thing to remember here is what was the clue that we wanted to resort to long division? It was we have a fraction that we're trying to integrate. What's the degree of the top? 2. The degree of the bottom was 2. Whenever the degree of the top is at least as large as the degree of the bottom, at least as large, could be larger, but it has to be at least as large, then sometimes this long division process is beneficial. All right, sometimes, okay? So it's worth giving it a try if, see here we just used direct substitution, right, and we didn't get very far, okay? So if just the direct substitution doesn't work, okay, then you can switch to plan B here and try long division if the degree of the top is at least as big as the degree of the bottom. Well, this is 2 and this is 2, so the degree of the top is at least as big as the degree of the bottom. So we're in a situation where the long division process can help, all right? Now, what am I going to do here, right? So what is the long division? Let me erase some of this stuff now, because all of that was just not wasted effort, right? But none of that's going to work. And let's do the long division. Okay, so here's the way long division works, right? You're going to write down, see in this fraction, we're dividing x squared plus 1 into x squared plus x plus 1. So write that down as a long division problem. X squared plus 1, we're going to divide that into x squared plus x plus 1. Okay? So just write that down like you did, long division with numbers, right, back in the 4th grade. I remember I don't know where they do it now, but I did it oh no, it wasn't 4th grade. I think it was 5th grade. Okay? So I did it in 5th grade, okay? And so write that down like a 5th grade long division problem, and you actually carry out the process like a 5th grade long division problem. So remember, when you're dividing numbers with long division, you take the digit on the far left here, right, and then you divide it into the first digit under your division bar, okay? So that's what we do here. I'm going to take the x squared and divide it into the x squared, okay? Let's write that down so we can see what that quotient is. So I'm going to take x squared and divide it into x squared. This x squared I'm going to divide into this one. All right? What is that? 1. What could be easier, right? Okay? So that's going to be just 1. So you're going to write that down as part of your quotient. Okay? All right, so we'll write that down. Let's make sure we put that 1 in the right spot. I think I'm going to put it right here because 1 is a constant, right? And this is the constant under the division bar. By the way, this quantity has a name. That's called the dividend, and this is called the divisor. That's just the terminology of division, right? So x squared plus x plus 1, that's called the dividend, and the x squared plus 1 is called the divisor. But if you don't want to remember those terms, right, this is what you're dividing into, and this is what you're dividing by, right? Okay, now what do we do with that 1 once we've written that down? Do you remember what you did in long division when you wrote that down? That first number above the division bar, what did you do with it? Yeah, you had to multiply it back through, right? Okay, and you wrote your product down here, right? And then what did you do? Subtracted, right? You're going to do the same thing here. So we're going to take the 1, and we're going to multiply it by x squared plus 1, and then we're going to subtract. It's just the same process. So let's do that. What's 1 times x squared? That's x squared, correct, right? And what's 1 times 1? 1. Now, put the 1 not here, okay, beneath the x, but put it here beneath this 1, because we're going to have to subtract, okay? So to subtract, you got to make sure you've got your terms lined up properly so you can subtract them. So put that 1 over here because you're going to add that or subtract that from this 1, right? You can't subtract that from x because those are not like terms, right? Okay. Now we subtract. Look, I strongly recommend, okay, that you think of the subtraction in reverse. Think of it as changing the sign and adding, okay? So you want to think of it as addition, not subtraction, because it's harder to think about subtraction than it is addition, all right? So let's change the signs. So I'm going to make this minus, and this I'm going to make minus, and then I'm going to add, all right? So what's x squared plus a minus x squared? 0. Yeah, you couldn't miss there, right? Okay, that had to 0 out. What happens to the x? Nothing, okay, because nothing is subtracted from that. What happens here, of course? 0, right, okay. So you end up here with, that's called your remainder, right, okay. So you end up with the remainder there of x. Now, in many instances, what will you do? You'll have to what? No, you don't take, not quite yet. Before we take it to the top, what do we do? You repeat the process, right? Okay. Remember, you have to repeat this process again, correct, right? So you repeat the process, repeat the process, repeat the process. Of course, somewhere you have to stop, correct? Okay. And how do you know when to stop? Well, in long division with numbers, how do you know when to stop this process? How do you know you can't divide, though? So what's the clue that you cannot divide? Fine, yeah, that's what I wanted to say, right. When the remainder is smaller than the, what's this called? Divisor, yeah. You know you quit when the remainder is smaller than the divisor, okay? Now, look, we can't use that same test here because these are not all just, these are not just numbers, right? These are expressions with variables in them. So how do we know when to quit? Good question. You quit when the degree of the remainder is less than the degree of the divisor, okay? So you look at degrees, okay? What's the degree of this expression? 1, because what's the highest power of x? 1. What's the degree of this expression? 2. So we're going to quit. We've already quit. We're done. All right? We've already quit this, okay? Because our remainder has degree less than our divisor. Now, how do you write your answer? In 5th grade, how did you write your answer for your teacher? What did you do with that? Yeah, I remember doing this. You put a little r up here, right? Okay? And, you know, so the way you read that is, okay, when I divide this into this, I get this quotient, and this is the remainder, okay? That was one way of writing the answer. But there was another way of writing the answer, and it's the second way that we're really interested in, okay? What this tells me is, what this long division told me is, when you take x squared plus x plus 1 and divide it by x squared plus 1, what you get is 1 plus the remainder divided by the original divisor. Okay, that's the other way of writing your answer in 5th grade for your teacher. Okay. And I remember we were, so probably you have the same recollection. I remember we were expected to do this both ways, but I wasn't never quite sure why we wanted to write it both ways. You know, why not? Wasn't one answer enough, right? Okay. And that's because when your teacher knew when you got to Calculus 2, all right, you wanted to write your answer like this, all right? That's how we want to express our answer. All right, now, okay, look, I've done no integration now. All of this is algebra. So when are we going to get back to the calculus? Well, we're going to do that right now, okay? So x squared plus x plus 1 over x squared plus 1, that can be rewritten how? What did I just learn? That can be rewritten as 1 plus x over x squared plus 1. Okay, that looks harder than the original problem, so why has that helped me at all? Okay, well, let's see. Is this really harder than the original problem? Here I have an antiderivative of a sum. Guess what? You can break that up into two antiderivatives, okay? So this is really the antiderivative of 1 dx plus the antiderivative of x over x squared plus 1 dx, okay? Now maybe I'm getting somewhere, because what is the antiderivative of 1? That's very easy, antiderivative. So we don't need any fancy natural logs here. What's the antiderivative of a constant? You just put the x on it. That's right. Yeah, okay. The antiderivative of 1 is going to be 1 times x. That's it, right? Okay. So we've made some progress here, because now we have something there, right? Okay. So part of our antiderivative is going to involve x. Remember, when you're integrating a constant, you just get the constant combined with x, right? Okay. Because what's the derivative of x? 1. Yeah, right, okay. So the antiderivative of 1 is x, right? Now, what about this one, though? Guess what am I going to do here? Substitution, that's right, okay? So I've not completely escaped substitution yet, right, okay? I have not escaped substitution, but now I've got a different substitution problem, and I'm hoping it's easier. All right, now, y'all can tell me how to do this like a knife through butter here. What am I going to substitute? Yeah, u for the denominator, right? So u is going to be x squared plus 1. So what's du there? dx, that's what? 2x. So dx is du over 2x, right? So we throw that in there. So I have x over u times du over 2x. This looks like what I just did, right? What happens here? The x's divide out. What am I going to do with the 2? Going to pull it out, right? So I'm going to pull that out. And is that any derivative hard now? This one? Is that hard? No. What's the antiderivative there? ln of what? Absolute value of u, right, okay. Now I can finally throw in my constant. But what is u? X squared plus 1, right? Is that what it was? Yeah, x squared plus 1. There, we're done. So we get this beautiful antiderivative, okay? X plus 1/2 the natural log of the absolute value of x squared plus 1 plus c. Welcome to Calculus 2, all right? This is just a taste of what the problems look like in Calculus 2. Okay, I'm not trying to scare you. This is the nature of the problems. All right. Okay. Nice antiderivative there. You can check that, by the way. Of course. How can you check your antiderivatives? I haven't really been emphasizing this in the class, but how can you check your antiderivatives here? Find the derivative. Sure, right. Find the derivative. And you're really good here at finding derivatives, right? So you can check these. You can check these. Do I have some room here? Not much. All right, but you can check your antiderivatives sometimes. Sometimes it really does get ugly, but in many cases it is possible to check your antiderivatives. So you don't have to rely on a website always to grade your problems for you. Let's see, if you take the derivative of this, what are you going to get? What's the derivative of x? 1 plus, then you're going to have 1/2 times, what's the derivative? The 1/2 will stay, but what's the derivative of natural log of absolute value of x squared plus 1? 1 over x squared plus 1 times what? Times 2x, the derivative of x squared plus 1, right? And then what's the derivative of that constant? 0, right. This is a constant, so its derivative is 0. So you end up here with 1 plus, these 2's are going to cancel, so you end up with 1 plus, it looks like x over x squared plus 1. Is that what I started with? Way back up here? After I did the long division? Is that what I started with? Yeah, right. Okay, so that was the correct antiderivative. As long as I did the long division right. Okay, as long as I did the long division right. All right. So let's try one. I have an example of this one on video. Okay, so there's a link to this in your integration homework, but we're going to do this one because one example of long division is not enough. Okay, but I'm going to help you get started, and then I'll let y'all finish it. So here we're trying to find the antiderivative of x squared plus 3x plus 2. Well, you can see it there, right? Over x plus 2. Is that what I wanted there? Yeah, they're probably like all of these in the homework. Okay, all right. Okay, so no, we're going to do this one. All right. So when we look at this one, this one's a little. There are two ways to attack this one, but let's do it with long division because that's our goal here is to practice long division. Okay. There's a shortcut to this problem which I just noticed, but I don't want to use the shortcut. All right. So let's try doing it using long division. So all right. So what would sort of clue you in that that maybe long division is the way to go here? Yeah, that's right. You're looking, you're saying, okay, here I have this is a polynomial expression divided by a polynomial expression, and the degree here is 2, and the degree here is what? 1. So maybe long division will benefit me here, right? Okay, so we'll give that a try. So we have to set up the long division problem. So I have x plus 2 divided into x squared plus 3x plus 2. All right, so see if y'all can do that long division. Just stop there at first, okay, and see if you can get through the long division, because if you're not able to get through the long division, then you're not going to get any further, right? Somehow I think I've changed this example, but it's okay. Mm-hmm. Yeah, in this one you can actually use synthetic division because of the form of the denominator. Okay, but synthetic division doesn't always work. So it's probably safer just to go through the whole long division process. They won't be in the problems. The long division won't be so complicated that it'll be hard to carry out. Okay, yeah. Someone was asking about, some people have done synthetic division before, right, which is a shortcut for doing long division, right? And that works in certain cases. And it will actually work on this problem, but it doesn't work in all cases. So I think just go ahead and do the full long division process. On all of our problems in the homework on a test, the long division won't be so terrible that that'll take you too long. Did you get it there? Janaya there, right? So, yeah, now, oh, I see. So you're finished there? So you came up with this? Right, so that integrand just reduces to what? Are you started there, right? Yeah, so how many times does x go into x squared? That's what you want to ask yourself. Oh, is that what you're doing here? Yeah, what's x squared divided by x? X. Yeah, it's x. So write the x up here above the x term, okay? Yeah, remember, what's x squared divided by x? X. Yes, right, okay? You got to get your algebra cap on here, right? Okay. So you have this. Huh, that's nice, right? So that's certainly a much easier integrand, correct, than the one we started with. Oh, yeah, right. So now you have just this easy integrand, right? Okay.
I'm pretty sure I did something wrong.
Yeah. So what's x into x squared? How many times does x go into x squared? What?
2 times.
No, write it down for me. X squared over x. Yeah, if you need to write it down, write it down. What's x squared over x equal to? What does that reduce to?
X?
Yeah, x. I think you were thinking it's 2 or 1 or something, but it's x. So x is what you write here. Yeah. Now multiply back through. Okay? Now multiply back through. All right, so you want to ask yourself, how many times does x go into x squared? How many times does x go into x squared? What? X. So you write x up here. Yeah, on the top. Put it above this x, though. Keep those things lined up. Yeah. Yeah. So erase this 2, right? Now multiply back through. Now multiply back through. So multiply x times x plus 2. Write that down here and subtract. Okay? Which is the same as changing the sign. What did y'all end up with there? You got stuff. Yeah, okay, so what does x go into x squared? Write it down.
Is it x?
X, yes.
That's what we got.
Yeah, so put it
That's
here.
3x.
Yeah, on top of the 3x, right. Yeah, just to keep things lined up. That'll keep you from making mistakes. Multiply back through. So when you multiply back through, what do you get? X squared, but you also had to multiply it by the 2. Yeah, x plus 2x, right? So write that down below. X squared plus 2x. Now change the signs and add.
Yeah, right. You said so that'll be a negative.
That'll be negative.
That'll be a negative.
Yeah.
So I add them.
Yeah.
So I say
0.
3x
What are you going to get there?
plus minus 1x or x.
X, right? And then you can bring the 2 down.
Bring the 2 down.
Yeah. Now do it again.
X plus 2.
How many times does x go into x again?
Can I just do it all at once? X plus 2 goes into x plus 2 at one time.
Yeah, you can do it all at once. So you have 1 there, right, at the end.
Yeah, 1.
So you end up with x plus 1.
Oh, okay.
Yeah, remember you had an x here, right?
Yeah.
So x plus 1. There it is, x plus 1. Yeah.
Why we just didn't use a quadratic equation?
Because we're not really solving an equation here.
Just like to try to separate our factors for x squared plus 3x.
Yeah, that one, that's why I said this is kind of a bad example because x squared plus 3x plus 2 will factor. Yeah, okay. So it would have been a better example had that not factored because this still would have worked. Yeah, okay. All right. But no, it's not always the secret because it won't always factor. Yeah, it won't always factor. Okay.
So I did that, but now it's like,
Yeah.
how do I...
Now you're done, right? Well, you're almost done. Now, so you know this antiderivative is the same as the antiderivative of just what?
Would it be x?
Yeah, just x plus 1, right. So all that reduces to just antiderivative of x plus 1.
Oh,
Yeah,
I guess
see,
it
right?
confused me on the other one.
No, we did the same thing, right?
Yeah.
We took this and plugged it in there, right? We took our quotient and plugged it in there, right? Okay. Yeah. Oh, the reason you're confused is because the remainder is 0.
Yeah.
Yeah, remainder is 0. Okay. Did you get a division there? Okay, so you got x there, right? And then did you multiply back through? X times x is x squared. X times 2 is 2x. Yeah, right. Okay. Yeah, so that should be x. This is gone.
Okay.
And then you can bring the 2 down.
Oh, so we're gonna do this.
Yeah, that's gone. Bring the 2 down. Now you repeat the process. Divide this into this.
Okay.
Yeah. Okay. Right. What'd you get? You're right. Yes, that's x plus 1. What'd y'all get? Yeah, perfect. Okay. All right, so y'all got through the. So let's do this one quickly because y'all got through the long division really well. What confused some people is this one ends up having a remainder of 0. Okay, so divide x into x squared. Again, if you need to, write that off to the side. X squared goes into x squared x many times. X many times. X squared over x reduces to x. So you have x here, now multiply back through. So you get x times x is x squared, x times 2 is 2x, right? Now you subtract. So change this to a minus, change this to a minus. You have x there. Now you can bring down the 2. Right? Now, you cannot stop here because this has degree 1 and this also has degree 1. You cannot stop until the degree of the remainder is less than the degree of the divisor. So go again, divide x into x, but that's so easy, right? X goes into x 1 time, right? And now multiply back through again. 1 times x plus 2 is x plus 2. Well, here when you subtract, of course, you're going to end up with 0, so you have to stop there. So your remainder is 0. This is a nice remainder of 0, right? So what that tells us now is that this integrand is really the same as x plus 1. X squared plus 3x plus 2 divided by x plus 2 is just x plus 1, okay, without any remainder. So you don't have to add on the remainder divided by the divisor. Okay, now that's easy to integrate, right? Okay, so you see now you got a really easy integration problem. So what is the antiderivative of x plus 1? Just take it term by term. What's the antiderivative of x? Antiderivative. X squared over 2, right? Okay, this is the power rule. Add 1 to the exponent. This is exponent 1. Add 1 to the exponent, you get x squared, and then divide by the new exponent. What's the antiderivative of 1? We just mentioned that a moment ago. It's what? X plus, and then your constant. See how easy that was? So it went really quick. Let me change the problem slightly and do it again, okay? But let's do that after the break, all right? Because this one was artificially simple because you ended up with the remainder of 0. Let's try one where the remainder doesn't end up as 0. That's a more interesting problem, okay? So let's come back at 10 after, and we'll do that quickly, okay? And I've got some more fun examples for you that are more complex like this. Okay, let me change this problem just a little bit and go back through it. So we're going to use just the same techniques, but let me change the denominator here to x minus 2 instead of x plus 2. So again, we're going to use the same technique. So, oh, sorry, that's supposed to be a 2 there. Again, we're noticing, right, that here we have a quadratic expression, degree 2, divided by this degree 1 expression. That's called a linear expression, degree 1. And so we're thinking maybe we can handle this through long division. So let's carry out the long division. Now, it won't quite work out so well, but it's still easy. So I keep writing 2 instead of a 3. So x goes into x squared x many times, right? And then we'll multiply back through. So x times x, of course, is x squared. X times minus 2 is minus 2x. And then we change the signs, right, and add. Same as subtraction. So 3x plus 2x is 5x, and then we can bring the 2 down, right? Okay, so now this is degree 1, this is still degree 1, so I need to repeat this division process. So x goes into 5x 5 times, right? And then multiply back through. So 5 times x is 5x, and then 5 times a minus 2 is minus 10. And now, again, change those signs and add. So now we end up with a remainder of 12. That has degree 0. A constant has degree 0. This is degree 1. So we know this is where we're going to stop, right? So our quotient here is x plus 5 with a remainder of 12. All right. Now let's rewrite the integration problem. So the integrand we can write as x plus 5, this quotient in the long division, right, plus 12, the remainder, divided by the original divisor, which was x minus 2. Okay. So in this version of the problem, the remainder is 0. So if you wrote 0 over x plus 2, that would just be 0. But here we have a positive remainder 12, right? And so we have to write x plus 5 plus 12 over x minus 2. Now, again, you can break this up, though, into different integrals. So you can write this as just the antiderivative of x plus antiderivative of x plus the antiderivative of 5, and then plus the antiderivative of 12 over x minus 2. But at the same time I'm writing down this antiderivative of 12 over x minus 2, I'm going to factor out the 12. Okay, so I'm going to put the 12 here in front, so I have 12 times the antiderivative of 1 over x minus 2. So you get those 3 antiderivatives. So it sounds like we've made a bad trade here, right? We traded 1 antiderivative for 3 antiderivatives. But actually, the 3, we made a good trade here because these are all easy to integrate, all right? So what is the antiderivative of x? Yeah, that's x squared over 2. That's using the power rule, right? You integrate this using the power rule. Add 1 to the exponent, divide by the new exponent. That's the anti-power rule, right? Okay? So we use the anti-power rule to integrate here. What's the antiderivative of 5? 5x, right? That also is actually the anti-power rule, okay? So the antiderivative of 5 is 5x. However, what's going to be the antiderivative of 1 over x minus 2? So we can go through the full process of doing that, but you're going to end up with, can you see what you're going to end up with here? You have the reciprocal of what expression? X minus 2. What is the derivative of x minus 2? 1. So you have an expression divided into its derivative, right? An expression divided into its derivative. So what does that automatically integrate as? Natural log, right? Okay. So you're just going to get quickly there. Don't forget the 12 that's out in front. 12 times the natural log of x minus 2. Now, if you want to, here you could go through the full substitution process. So you could substitute u for x minus 2 and go through those steps. You'll end up with 12 times the natural log of x minus 2. Okay, but you can also see how this is going to integrate in this case, because this is pretty easy, because you have this expression and then in the top here is its derivative. Okay, all right, so there's another similar but a little bit more complicated example, right, of using long division. We're not going to use long division in this example. Okay, and the reason long division is not going to work well here is the degrees are wrong. All right, what's the degree of the top here? 1. But the degree of the bottom, if I multiplied out x plus 1 times itself, so if I expanded that product, x plus 1 times x plus 1, which I'm not going to do, but if I expanded that product, x plus 1 times x plus 1, you would ultimately end up with what term in that product? You're going to get x what? Squared. So that means the bottom has degree what? 2, right? Okay, so you have degree 2 in the bottom and degree 1 in the top, and that is not good for long division. Okay, remember, for long division to be effective, the degree of the top has to be at least as large as the degree of the bottom. So this is not a long division problem. Well, okay, so let's just try plain old substitution here. All right, so any suggestions there? Yeah, that's right. Okay, that's what I'm thinking too. All right, let's just let u be x plus 1, and let's see what happens here. All right, so let's see. When u is x plus 1, then wow, we get a nice dx here, right? Because what is du dx? 1, right? So what's dx? Du, right? Okay. So we end up here with this. 2x over x plus 1 is u, right? U squared times what? Du, right? Okay. Because du is dx, right? Oh, darn. All right. That did not have a happy ending so far, correct, right? Because I cannot proceed just the way this is written, because what's wrong? Yeah, it's not in the right form, because why is it not in the right form? You have not canceled out your x's, right? Okay? Yeah. If you're going to see, our goal here in doing substitution is to change the variables completely from x's to u's. And at the same time, when we do that, hopefully we will end up with a simpler integrand, right, that we know how to integrate. But I didn't even achieve my first goal. I did not cancel out I didn't even manage to cancel out the x's here, right? Okay, so I'm really sort of, just not in a good space, right? Okay, haven't achieved what I want. All right, but so here we're going to have to think just a little bit more carefully about our substitution. All right, let's go back to this equation, okay, where it says u is equal to x plus 1. Now, that's an equation. That equation is solved for u, all right, because that's the way I wrote it down. I just wrote u equals x plus 1. But that equation can also be solved for x. So what is x equal to in this equation? U minus 1, right, okay? So I also know, well, I know u is x plus 1, but I also know that x is equal to u minus 1. That's really helpful, maybe, okay, because now I can put the u minus 1 here in where I have the x, you see, okay? So kind of a two-step substitution there. I substituted u for x plus 1 here, right? But then here I substituted u minus 1 for x, all right? All right, let's put that in. Now, maybe that's not going to ultimately get me anywhere, but at least I got rid of the x's, okay? So let's do that. So we have, at the same time, what can I do with this 2? Take it out, right? You can factor out the constant. So let's try factoring that out as well. I'm not sure that I need to do that, but let's just go ahead and do that. So what was x? U minus 1, right? Over, and then we have u squared, correct? All of this times du. All right. That's still not exactly what we want. You can't do long division here either with the u's because the degree of the bottom is 2 and the degree of the top is 1. But here we have to think about algebra a little bit more. All right, so we have to rely on our algebra skills again. I can break this fraction up into 2 fractions. See, right? Okay. I can write this as u over u squared, and then I can write it as minus 1 over u squared. So let's try that and see if that's helpful. So I have 2 times the antiderivative of u over u squared, and then, well, let me not break it up into 2 antiderivatives yet. So I have u over u squared minus 1 over u squared, right? And, okay, that's looking promising because, of course, what can I do with u over u squared? You can reduce that, right? That reduces to what? That's 1 over u. And I'm going to break this up into two different integrals at the same time, right? Because I can integrate this term and this term separately. So I'm going to break this up as minus 2 times the antiderivative of 1 over, here, it should have a du here, and then 1 over u squared du. Can you all see that u? See the 1 over u squared. And since I broke it up into two different integrals, make sure you distribute the 2. So I have to put the 2 in front of them, right? How does that integrate, though? That's a very basic one. What's that? What? That's natural log of u, right, okay? That's the one we've been doing all the time, right? This is the same as du over u, if I put the du in the numerator. So this integrates instantly. So I've made progress. So that's promising. So that integrates as 2 times the natural log of u. Wow. All right, so now I'm stoked a little bit, okay? What about this one? Can I integrate this one? Now, that's not an integrate using natural log, because that's not 1 over u to the first power. That's 1 over u squared. But how can you rewrite 1 over u squared? Don't need to do that yet, okay? I am going to do that eventually, but not yet. But you can rewrite this using a negative exponent, right? 1 over u squared is the same as what? U to the minus 2, right, okay? So this is minus 2 times the antiderivative of u to the minus 2. And how can I integrate u to the minus 2? What rule? The anti-power rule, right, okay? I can use the anti-power rule. What does the anti-power rule say? You add 1 and divide by that new exponent, correct? Okay? This one I can integrate using anti-power. I cannot use, remember, I cannot integrate this using the anti-power rule, right? Because 1 over u is u to the minus 1 power, and when you add 1 to the exponent, you get 0, so you cannot divide by 0. But here, when you add 1, your exponent is minus 1, and you can divide by minus 1. So this we can integrate using the anti-power rule. So do not forget about the anti-power rule. That's really the most useful integration rule. So I have 2 natural log absolute value of u. And now let's see, y'all tell me here. This is minus 2 times what? What's that going to be there? U to what? Negative 1 divided by what? Divided by minus 1, right. And now we can throw in the constant. So actually the integration now is finished, see? All of the rest of this is just making things look nice with algebra. Let's see here, 2 divided by minus 1, that's going to be plus 2, correct? So I can write that as plus 2. And what's u to the minus 1 power? How can you rewrite that? 1 over u, right. So you get 2 times 1 over u plus the constant, right? And now let's undo our substitution. So we have 2 times the natural log of absolute value of, I already forgot what u was. What was u here? Wow. Let's go all the way back up here. What was u? X plus 1. So you have 2 times natural log of x plus 1 plus, this looks like 2 over u, which is x plus 1. No absolute value there, plus a constant. Okay? Woo! All right. Neat. So there, just no long division, just plain substitution worked, but we had to do a little bit extra, right, when we were going through the substitution to make sure that we eliminated the variable x. All right, well, let's try another one, okay? All right, so this one we're just going to do with substitution. This has nothing to do with long division, right, because of this this natural log. So we're just going to use plain old substitution, but y'all have to tell me what you think I'm going to substitute for. Yeah, that would be my choice there. I'm going to let u be natural log of x. What kind of clued you in that it might be good? Well, actually, maybe that's wrong, but that's what I would try first. Okay, I think that's right, but I'm not sure. I have to see. Now listen, if I say, in class, I'm not sure what the answer is, I mean that. I'm not sure what the answer is at this point, right? So look, but that's very typical, even for me, because integration is a trial and error process. Okay, you try something, it may work fine. Okay, but it may not work, and then you may have to try something else. All right, then that goes for me as well. Okay, that's just the nature of integration. Differentiation is not like that, right? Differentiation, you have these very set differentiation rules you can follow, right? Okay, but integration is. It's not like I can look at an expression and say, oh yeah, this is the steps I have to follow to find this antiderivative. Okay, it's trial and error. So now you might say, well, it's going to take me forever to do a single problem, right, or to finish my homework assignments. No, because after some practice, your intuition will become good, and you will recognize immediately, oh, this is what I should try first. Okay, all right. So we already had a suggestion of let u be natural log of x. That's what I would try first. But what was kind of your intuition that maybe natural log might be the thing to try? Why not x times natural log of x? That's the whole denominator. Maybe that would work too, okay? But why just natural log of x? Here's what I would see, okay, as to why that might be the right choice. Because what is the derivative of natural log of x? 1 over x. And notice that in this expression, you have 1 over x, okay? So that kind of tells me, that's kind of suspicious, all right? That might be something to try, all right? But maybe that's maybe that won't get us anywhere, right? Okay. All right. So we're going to let u be natural log of x. So what is du dx? What did I just say? 1 over x, right? Okay. Now we have to solve this equation for dx. Can I solve that equation for dx? Multiply both sides by dx, right? And that gives us what? Du is dx over x. But I just have to have dx, right? So how do I get to just dx? Multiply both sides by x? Yeah. So you get finally there dx is x times du. Okay. Now we are ready for the substitution. So I have 1 over x times natural log of x, but that's u, times what's dx? X du, right? Yay! So did our substitution work? Yes, right, because exactly what we wanted to happen happened here, right? The x's are going to cancel, you see, okay? The x's are going to cancel, so you'll end up with an antiderivative that just has u's in it. That's one thing we want. And the second thing we want is we want it to be an easy antiderivative, right, okay? We want it to be an easy antiderivative. Is this one easy to integrate, though? Yes. It's just natural log again, right? So there we are, back to that very familiar antiderivative here, natural log. But now let's undo the substitution. What is u? Natural log again. So you get there the natural log of x, okay, plus a constant. So funny looking expression for the antiderivative, but that's it, okay. 2 natural logs there. Composed with one another. All right, so I got some videos for you here, okay? So I have a video of this one, so we won't go through this one in class, all right? But I have a video of that, so you and again, there's a link to that in the second homework assignment, so you can look at that example as a further example of using integration by substitution. What do you think there might be the nice substitution here in this problem? Again, I'm going to let u be natural log of x, not u be x, but I'm going to let u be natural log of x. And again, what's the tip off there that might work well? You always want to think about the derivative of your substitution, okay? So what is the derivative of natural log of x? 1 over x. And notice that in that integrand, we do have 1 over x because you're dividing by x. So that's the same as multiplying by 1 over x. So so that kind of gives me a hint that that's probably the right substitution. But sometimes the substitutions are very not clear. Okay, all right. So sometimes they're just not easy to see. All right, especially without having seen some examples. So we're not going to go through this entirely today because this takes a long time, but I'm going to start with this one next time as an example. But I will tell you what to substitute here. But if you were just facing this antiderivative for the first time, you wouldn't really be expected to know how to do this, all right, without having had some example to sort of clue you in. Someone, did you raise your hand there?
So is a problem like that going to be on the homework too then?
There is a problem like that in the homework, okay? There's a problem like that in the homework. And so we'll get a chance to, but I'm going to show you what substitution to use here, but I'm not going to go through the full thing until Monday, okay? But there is, I think, one problem like this in the homework, and it will work very much like this one. The good thing about the homework, though, is in this section, not in every section, but in this section, since you're just practicing integration for the first time in the class, in that homework, it often tells you, try this substitution. Okay, and so I'm going to tell you here, the substitution to use here is just the denominator, just what we've been doing in the past. Okay, just try the denominator. All right. But that's just the beginning of the fun in this problem. Okay, so but that is ultimately the correct substitution. Okay, all right. So we'll start with that one next time, and then I have a video for the next exam. Yes, I do. So here's a kind of a similar example. There also is a problem like this in the homework. But I have a video of this one linked to the homework. So when you encounter this problem in the homework, take a look at the video first, okay? And that will help you. You'll immediately recognize the homework problem that looks like this one. Take a look at the video, and that will help you a lot. Again, the substitution, I think, is very straightforward here. It's just the denominator, okay? But that's just the start of the fun. No, we're not done yet today. We have a few minutes left. Okay. All right. All right. Let's finish off with two easy examples. These look hard, okay, but they're not. All right. So in Calculus 1, I know you learned the antiderivative of sine and cosine. All right. Not derivative, but antiderivative, okay, of sine and cosine. And those are easy because, the derivative of sine is cosine, so it's easy to know what the antiderivative of the cosine is, right? And the derivative of the cosine is minus the sine, so that helps you understand what the antiderivative of sine is, all right? But what you probably didn't learn in Calculus 1 is what is the antiderivative of the tangent? That was kind of just left out there as, just never answered, right? What's the antiderivative of the tangent? Or, similarly, what's the antiderivative of the cotangent? And then the other two trig functions as well. What's the antiderivative of the secant? And what's the antiderivative of the cosecant? Well, the reason those are left off is, you'll see in this example, we're going to find the antiderivative of the tangent function. Okay? See if I can remember how to do it. So we're going to find the antiderivative of the tangent function. All right, so I think you won't have trouble with this. All right. All right. So as we often do when we're working with trig functions, let's rewrite the tangent in terms of sine and cosine. So what is the tangent in terms of sine and cosine? Yeah, that's sine of x over cosine of x, right? And now what I'm going to do is I'm going to make a substitution. Maybe not the one you would think of, but maybe it is, because it's the one we've been using a lot here in these notes. I'm going to substitute for the denominator, so I'm going to let u be cosine of x. I think this is correct. So I'm going to let u be cosine of x, and now let's differentiate. So what's the derivative of cosine of x? Negative, don't forget it's negative sine of x. So when you solve for dx, you get du over minus the sine of x. Be careful about that. All right, now let's Now let's substitute. So I have sine of x over u, because u is cosine of x, and then dx is du over minus the sine of x. And what nice thing happens here? Yay! The sine of x's cancel out just perfectly, and notice the minus sign is here though, so I'm going to factor that in front. So I have minus the antiderivative of du over u, and but of course now y'all know exactly what that is, right? That's what? That's natural log of absolute value of u, right? Okay. But what was u? Cosine of x. So there's the very unexpected answer. That's why you didn't learn this in Calculus 1, okay? All right. The antiderivative of the tangent is minus the natural log of cosine of the absolute value of x, okay? All right. Antiderivative, what's the derivative of the tangent? Derivative, secant squared x, right. Yeah, the derivative of tangent is secant squared x. But the antiderivative is minus, and it involves natural log of absolute value of cosine of x. All right, so we could pull exactly the same trick with cotangent. Write that as cosine over sine, okay? Make the substitution, and you can write down also a similar formula for the antiderivative of the cotangent. So, actually now, with our knowledge of natural logs, we can find the antiderivatives of all of the trig functions. Yay! So we'll now have a complete table of not only the derivatives of all of the trig functions, but also the antiderivatives of all of the trig functions. And here they are, okay? So there's the one we just learned. The antiderivative of the tangent is minus the natural log of absolute value of cosine. This is what happens when you do the cotangent. You get not negative there, just natural log of sine, okay? Secant now is a little bit harder to derive, but you can also find the antiderivative of the secant, and it also involves natural log. But it turns out to be natural log of secant plus tangent. All right, so I'm not going to go through the steps of finding the antiderivative of the secant, but there it is, and then there's the antiderivative of the cosecant. Very similar formula, right, as you might expect. So there's our complete table now. Once we have knowledge of the natural log function, we can build a complete table of the antiderivatives of the trig functions. Remember, this might be an expression, though, involving x, not just x. So this could be secant of, x squared plus 2 or something more complicated, right, than just plain x. All right. So there we have it, right? So now we know the antiderivatives of all the 6 trig functions. Look, the two that you're probably only going to remember are these two because they're so easy, right? You're less likely to memorize these, okay? So I'm just thinking you're not going to memorize these, but you will need to know them from time to time. So these are going to be things that you need to know where to find them. Here they are in the notes, right here at the bottom of these notes. This is from the book, though, so you can also find this in the text, but I forgot to write down the section. So this table is from the text. But on a test, right, these are things that you may want to include on your survival card, okay, right, in case you need to have those at hand, right, yeah. Mm-hmm. Yeah, that's right, it's front and back. Okay. All right, so now we know we certainly know this one, right, and these two. I'm just telling you those, right? So now you've seen the antiderivatives of the 6 trig functions. Okay, well, so next time we're going to start with our on Monday. Is it Monday? Yeah, Monday, right? We're going to start with that ugly example, and then we'll go on to section 5.4. All right. All right. So I'll see y'all then. Keep working on your homeworks. Have a good weekend.